All right, in my last video, I talked about the two main branches of calculus. Differential calculus or topics dealing with the tangent line problem, and integral calculus, or problems dealing with the area problem. I want to focus specifically now on the tangent line problem. And I want to take a different spin on our formula for the slope of a line. M equals y2 minus y1 over x2 minus x1. Okay, so here's our formula from algebra for the slope of a line through 2 points. So let's look at quadrant 1 in the xy plane, and let's look at some function. Some function, we'll call it f of x. Now, let's look at the slope, not of a tangent line, but let's look at the slope of a secant line, the slope of a line through 2 points. So let's say here's point number 1, and here's point number 2. And so let's say this first point has an x value, we'll call it x, and the y value would then be f of x. And let's say let's use blue here. Let's say the horizontal distance between these 2 points is delta x. Delta means change in, so that's the change in x. So this second point, instead of calling them x1 and x2, let's say we have these two x values that are a distance of delta x apart, or delta x is the distance between these 2 points, or these two x values. So this x value would be x plus delta x. And if the x value, so let me erase this for now, if the x value of this second point is x plus delta x, then the y value would be symbolically f of x plus delta x. Okay, so we have 2 points. Our first point is x comma f of x. That's point number 1. And then our second point is x plus delta x comma f of x plus delta x. So let's apply the slope formula to these 2 points. So what that will give us is the slope of this secant line. The slope of the secant line. Okay, so slope of the secant line is y minus y divided by x minus x. That's what the slope formula tells us. So our first y value, our second y value, so it should be f of x plus delta x minus f of x. That's the same as saying y2 minus y1, and this is divided by x2 minus x1. So x2 would be x plus delta x minus x. Okay, so we're calling this x1, y1, and this is x2, y2. Okay, so we've simply just symbolically given the slope formula using function notation. Instead of x and y, it's x and f of x. Okay, so if you look at the denominator here, we have a positive x and we have a negative x, so those two will cancel. Okay, so the slope, that should be black, the slope of the secant line is f of x plus delta x minus f of x, all divided by delta x. Okay, Now, we call this, let's have a little bit more room here. We call this the difference quotient. And what the difference quotient is the slope of the secant line through any 2 points on the graph of a function. And this is equivalent to saying y2 minus y1 over x2 minus x1. We're just using function notation. Now, what happens when we transition from pre-calculus to calculus, or when we transition from the secant line to the tangent line? Well, the tangent line, we have 1 point, not 2. So, what that looks like. So, let's think about, so here's our function, f of x, and here's our point, x, comma, f of x. There's our first point. Now, what you could think about is this second point, x plus delta x. Well, what happens, let's say let delta x get infinitely small. Now remember, delta x is just the horizontal distance between these two x values. So let's say we'll fix this x value, and this one, let's say this x value is movable. So we'll move it this way. So delta x is getting smaller and smaller. When we make delta x a little bit smaller, this point moves to about right there. We let delta x get even a little bit smaller after that. The point's here. So this secant line for a smaller delta x, or this secant line for an even smaller delta x, or let's say delta x is even smaller. So this secant line for a smaller delta x, the slope, so if you look at the slope of those secant lines, when delta x is getting smaller and smaller, or these 2 points on the graph are getting closer and closer together, the slopes of those lines are getting closer and closer to the slope of the tangent line. So this red one, this is the tangent line. So as delta x gets infinitely small, you can think about this point here, or this x value here, moving closer and closer to this x value. So the distance between them gets infinitely small. Well, this point sort of slides along the function and eventually overlaps this point. And so once that happens, you no longer have 2 points, which means you no longer have a secant line. So as delta x gets infinitely small, what happens is the secant line, or the line crossing through 2 points on the graph of your function, gets closer and closer and eventually becomes the tangent line. And to sort of express this formally, we're going to use what's called the limit. And so what we'll say is, now we'll dive a lot deeper into this topic a little bit later, but what we could say is, if the slope of the secant line is equal to f of x plus delta x minus f of x all divided by delta x, then the slope of the tangent line is equal to, well, it's equal to what you get when delta x gets infinitely small, or when delta x gets infinitely close to 0. And our notation for that is LIM for limit. So it's the limit as delta x approaches 0 of f of x plus delta x minus f of x all divided by delta x. So again, this is a topic from pre-calculus. This is a topic from calculus. Okay. Now in the next couple of videos, we'll talk more and more about this idea of a limit. But just before we talked about individual specific problems, I wanted to talk about this idea of a limit as our way of transitioning from a secant line to a tangent line, or more specifically, the slope of the secant line, meaning you have 2 points, to the slope of the tangent line, meaning you have 1 point.